The Nicol Prism is a very useful polarizing device made from calcite crystal, which derives its name from its inventor, William Nicol. The Nicol Prism was invented way back in 1820. It is made in such a way as to remove one of the two refracted rays by total reflection inside the prism. There are several different forms of the Nicol Prism, but we shall describe here one of the commonest ones. To create the Nicol Prism, first a calcite crystal about 3 times as long as it wide is taken. The acute angle in the principal section of a calcite crystal is at 71 degree. In the next step, this crystal is cut down and polished to a more acute angle of 68 degrees. In the next step, the crystal is cut apart along A', D' in a plane perpendicular to both the principal section and two end faces. The two cut surfaces are ground and polished optically flat and then cemented together with a material known as Canada balsam. The Canada balsam is a clear transparent substance having index of refraction midway between the index of the ordinary and extraordinary rays inside the calcite crystal. The index of refraction for an ordinary ray is 1.65836 and that of the extraordinary ray is 1.48641. The index of refraction of Canada balsam is 1.55, which is an average of the values of NO and NE. Let us now analyze the working of the Nicol Prism. The unpolarized light is allowed to fall onto the crystal like this. The Canada balsam is optically denser for the E ray and rarer for the O ray. The E ray, therefore, will be refracted into the balsam and on through the calcite crystal. The O ray, on the other hand, for large angles of incidence, will be totally reflected. The critical angle for total reflection of the O ray at the first calcite to balsam surface is about 69 degree. This corresponds to a limiting angle SMSO equal to 14 degree. If this angle is greater than 14 degree, then some of the O rays will also be transmitted and come out of the face CD'. The E ray in a Nicol prism also has an angular limit, beyond which it is totally reflected by the Canada balsam. This is because the index Ne equal to 1.486 applies only in the special case of light traveling at right angles to the optic axis. We know that along the optic axis, E rays travel with the same speed as O ray, and therefore the index is same as that of the O ray, which is equal to 1.65836. For intermediate angles, the effective refractive index of the E ray lies in between 1.486 and 1.658. Therefore, there will be a maximum angle SMSE beyond which the balsam will be optically dense than the calcite, and there will be total reflection of the E vibrations. That means that the E vibrations will also be reflected by the Canada balsam and come out along with the O rays from face BD'. Therefore, the prism is so cut that the angle SMSE is equal to 14 degree. For these reasons, a Nicol prism is a unidirectional device. That means that light can enter from face A-B and then leave from CD and BD. Light cannot enter from face CD and then leave the faces A-B and BD. We'll now discuss the action of a Nicol prism as polarizer and analyzer. For studying the optical properties of transparent substances, two Nicol prisms are used, one as a polarizer and the other as an analyzer. When two Nicol prisms are placed adjacent to each other, one of them acts as a polarizer and the other as an analyzer. If unpolarized ray of light is incident on one side of the polarizer, a linearly polarized E-ray emerges from the polarizer with its vibration direction lying in the principal section of P. Now, to analyze the state of polarization of the ray that is emerging from the polarizer, we can use the analyzer. The principal section of the analyzer is parallel to that of the polarizer P. Therefore, the E-rays will pass through the analyzer and then come out of the other face of the analyzer. Now let us see what happens if we gradually rotate the analyzer A. When we rotate the analyzer, the intensity of the E-ray decreases in accordance with Malus law. The second figure shows us what happens when we rotate the analyzer. Now, when we gradually rotate the analyzer, its principal section at some point becomes perpendicular to that of the polarizer P. In this position, the ray behaves as O-ray inside prism A and is totally internally reflected by the Canada balsam layer. Hence, no light is transmitted by the prism. In this configuration, the two Nicol prisms P and A are said to be crossed. If the Nicol prism A is further rotated through another 90 degree, the intensity of light emerging from A will go on increasing. The intensity will become a maximum when its principal section is again parallel to that of the prism P. Thus, the prism P produces linearly polarized light while the prism A detects it. Hence, the prism P is called a polarizer and the prism A an analyzer.